Hi friends, today I am giving lecture on topic examples of singularity of a function. Okay, myself Santosh Pagal. Okay, see main point of this lecture analytic function. We will going to discuss in this lecture singularity of a function. Before going to that point, we will see some basic concept which is very useful to see which type of singularity of that given function. Okay, first to see what is analytic function. Complex function fz is said to be analytic in a domain D if it is analytic at each point of that domain D. Okay, as you know, also function fz is analytic at a point means what? It is analytic not only at a point but also in some neighborhood of that point. Okay, this is the simple definition of analytic function at a point. Okay, now we see first definition of zeros of analytic function. Zeros of analytic function means what? If we find values of z such that f of z is equal to 0, then such values of z we can call as a zero of an analytic function. Okay, what is the definition of zeros of analytic function? We have to find those values of z which makes function vanish or which makes function zero, function value zero. Okay, that values of z is called as a zero of an analytic function. Okay, then in the neighborhood of zero of function at point z is equal to a of order m, function can be written as like this: f z is equal to z minus a raised to m into phi z. Okay, and this function has zeros at z is equal to a of order m, and this function phi of z is analytic and non-zero at z is equal to a in the neighborhood of z is equal to a. If this function phi of z becomes 0 at a point z is equal to a, then this function fz has 0 of order m plus 1 at a point z is equal to a. That's why this function phi of z must be non-zero at a point z is equal to a. This is the simple definition of zeros of an analytic function. Now we will go next point to the next point. Next point is what? Singularity of a function. Singularity is what? Singularity is not what? A singularity of a function is a point at which function increases or vanishes to be regular or analytic. Means those point our function becomes not meaningful in general way we can say. Okay, suppose we are having function if z is equal to 1 upon z plus 1. If we put z is equal to minus 1 in this function, then it becomes no meaning, because if we put in function 1 upon z plus 1, z is equal to minus 1, we get 0 on the denominator. If 0 obtained in the denominator, then it has no meaning. 1 upon 0 is infinity. So this function has no meaning. So such point is called as a singular point. Okay, you may say singularities. Okay, see definition: singularity of function is a point at which function increases to be analytic or regular. Okay, this is the another name of analytic function. We can call regular or analytic sig. Now uh, after a singular point, that point is called as a singular point. Now there are mainly two kinds of singularities. One is isolated and another is a non-isolated singularities. If z is equal to a is a singular point of function fz, and there is no other singularity within a small circle surrounding the point z is equal to a, then z is equal to a is said to be an isolated singularity of function fz. Otherwise that point is called as a non-isolated singularity. Meaning of this statement is that suppose we are having function fz, and that function has a singular point z is equal to a. If there exists a small neighborhood around that point z is equal to a, that neighborhood does not contains any other singularity inside that point, sorry, inside the circle. Okay, neighborhood nothing but we can take any circle, triangle. Okay, if we draw a circle around that point and that circle does not contains other singularity, okay, then if such a neighborhood exists there, we can say that singular point is a isolated singular point. Okay, if we next definition is that non-isolated singularity. Non-isolated is what? Suppose we are having function fz, and function fz has a singularity at a point z is equal to a. If there does not exist a neighborhood or a small circle around that point, around a point z is equal to a, it involves every time at least one point other than z is equal to a. Okay, in every neighborhood it contains a singularity other than that point, then that singular point is called as a non-isolated singular point or non-isolated singularity. See example here, example number one, f of z is equal to z upon z into z minus 2. Okay, is analytic everywhere. As you know, if function fz is analytic everywhere, suppose we are taking another function gz is analytic everywhere, then if we find a rational function fz upon gz is again analytic everywhere except zeros of the denominator. Okay, if denominator becomes zero, it has no meaning. Okay, here z is analytic everywhere, and this function z upon z minus 2 is again analytic everywhere, and this fraction is again analytic everywhere except zeros of the denominator. Okay, so these zeros of denominators are z is equal to 0 and z is equal to 2. Therefore z is equal to 0 and z is equal to 2 are the only singularities of the functions. Okay, no other point 0, no other points other than 0 and 2 becomes that becomes a denominator 0. So 0 and 2 are the only singular point of the function. So there are no other singularity of the z in the neighborhood of z is equal to 0 and z is equal to. If we draw a small neighborhood around the point z is equal to 0, that neighborhood does not contains singularity other than that point. So z is equal to 0 is a isolated singularity. Also z is equal to 2 is also isolated singularities, because here there is only two singularities 0 and 2. If we get if we find a distance between these 2 points is 2, if we take a distance 1 and draw a circle around point 2, that point does not that circle does not contains singularity other than 2. Okay, so z is equal to 2 and z equal to 0 are the isolated singularity of this function. Okay, this is the example number one. In this example we found that 0 and 2 are the singular point, isolated singular point of this function. See example number 2. Here in example 2, we are considering function 1 upon tan pi by z. This is the function on the numerator. This is the constant function is identity everywhere. Now for this rational function, problem occurs in the denominator, zeros of the denominator. Let us find first where that function becomes a 0. Okay, what are that point? Tan pi by z is equal to 0, that is pi by z is equal to n pi. Okay, tan, as you know, tan z nothing but sin z upon cos z. Zeros of sin z, zeros of tan z nothing but zeros of the sin z, and zeros of sin z is a n pi. So zeros of tan pi by z is nothing but n pi. Solve this equation, we get z is equal to 1 upon n, where n is 1, 2, 3, and so on. We may take negative integer also. Z is equal to 1 upon n, where n is equal to 1, 2, 3, and so on. So z is equal to 1, 1 by 2, 1 by 3, and so on. Z is equal to 0 are the singular point of the given function. Okay. uh, Out of these singular point, 1, 1 by 2, 1 by 3, up to so on, all these singular points are isolated, because we are considering, suppose we are dealing with this point, z is equal to 1 by 2, distance between 1 and 1 by 2 is 1 by 2. If we draw a circle of a radius 1 by 4, center is 1 by 2, that circle does not contains either point 1 or point 1 by 3. In this way, we can easily see all these points 1 by 2, 1 by 3, all these singular points are isolated. But if we deal with this point, z equals 0. Okay. If we draw very small neighborhood around that point, that neighborhood contains at least one singular point other than itself. Okay, so z equal to 0 is the non-isolated singularity of this function. Okay, so z is equal to 1, 1 by 2, 1 by 3, z equal to 0 are the singularity of the function, all of which are isolated except z is equal to 0, because in the neighborhood of z equal to 0 there are infinite number of other singularities. Therefore z is equal to 0 is non-isolated singularity of this function. Now see kinds of singularities, types of singularities. There are three types of singularities. Number one, removable singularity. Number two, pole. Number three, essential singularities. So definition of removable singularity first. Function fz has a removable singularity at the point z is equal to a. If it satisfies this condition, limit z tends to a, fz not equal to f of a. Next, definition of pole. Function fz is said to be pole at a point z is equal to a of order 1 if there exists positive determinant such that limit z tends to a, z minus a raised to m fz exists. Note, note, if fz has a pole of order 1 at a point z is equal to a, then that pole is called as a simple pole. Next, third type of singularities is essential singularities. Function fz has a singularities other than pole and remove the singularities, then that singularity is called as a essential singularities. Okay. Now there are some theorems. I am not giving you proof of that theorems. I am directly using that theorems for finding which type of the singularity of the given or what type of the singularity are there for the given function. Okay, these 9 theorems are very important. Okay, you must remember all these theorems in order to find which type of the singularity of the given function. Okay, number one theorem. I am here just reading that all that theorems. Okay, you can write this theorem. Okay, remember this theorem. These theorems are very important. Okay, first theorem: if fz has a pole at a point z is equal to a, then mod fz tend to infinity as z tend to a. This is the statement. If fz has a pole at a point, then mod fz must be tend to infinity as z tend to a. Contrapositive statement is that if mod fz does not tend to infinity as z tend to a, then fz has no pole at a point z tend to a, as no pole at z is equal to a. Theorem number two: if analytic function has a pole of order m at z equal to a, then 1 upon fz has a 0 of order m at z is equal to a, and conversely. Okay, function fz has pole of order m at z is equal to a, if we take a reciprocal of that function, it becomes 0 of same order at same point, and conversely. Theorem number 3, zeros are isolated. Number 4, poles are isolated. Okay, limit point of zeros of an analytic function is an isolated essential singularities. Number 6. Okay, this theorem number 5 is also very important. If we are having an analytic function, we have to find which type of the singularities are there. That time we are just finding the zeros of that function and limit point of that zeros, and based on that limit point we can easily say that limit point are nothing but isolated essential singularities. If a given function having some poles, okay, or infinite number of poles, from that also we can say that limit point of the poles of a function is a non-isolated essential singularities. For that time we are using the theorem number 6. Theorem number 7, if a single valued function has no singularities other than poles either in finite part of the complex plane or at infinity, then fz is a rational function. A function fz which is a regular everywhere except at infinity, where it has a pole of order n, is a polynomial of degree n. Function which has no singularity in a finite part of the plane or at infinity, okay, function which has no singularity anywhere, then that function must be a constant. Okay, and these 9 theorems are very important. That will be helpful for finding which type of the singularity of the given functions are. Okay, this is all about theory of singularity of a function. In the next lecture, we will see how to use these theorems, definitions for finding the singularity of the function. Okay, one more things. Uh, Test of detecting singularities. Okay, see, uh, we are using that 9th theorem. We are also using this test for detecting singularity of the function. First test for removable singularities. See, removable singularity. If limit z tends to a, f of z exists finitely, okay, then z is equal to a is a removable singularities. If we are having function f z, we are checking at the point a which type of the singularity, just to check limit z tends to f of z. If it exists finitely, means we are getting some finite values, then we will say that point function has removable singularities. Number 2, poles. uh, the poles we can use either a or either b. Okay, c, what is the point a? If limit z tends to a, f of z tend to infinity, then z is equal to a is a pole of fz. Or b part, in b part, see, here is what there are there are finite number of terms in the principal part of fz. Means what? If we find a given function fz as a if we find the Taylor series expansion or Lorentz series expansion of this function fz, if we write that function in a Taylor series, uh, it has a it contains two parts. One part is the analytic part, and other part is a principal part. In that principal part, if there are finite number of terms, we can say that function has a pole at that point. Okay, see here example. Limit z tend to a, z square minus a square upon z minus a is equal to infinity. Solve this limit. On the numerator, here is a z square minus a square. This can be written as z minus a into z plus a upon z minus a. Z minus a becomes cancel, remains with z plus a. Apply limit, we will get infinity. Okay, by using a part at the point of z equal to a, this function has a pole. Type number 3, essential singularity. Again, a part, limit z tend to a, f of z does not exist. Okay, does not exist, then z is equal to a is a essential singularities. Okay, you may say if that point a given function has no removable singularity or no pole, then it must be scissor singularities. Okay, but there is a difference between a limit being infinity and limit not existing. Okay, limit here is what, limit being infinity. Here is what, limit does not exist. If limit does not exist, that time we can say that point a function has a essential singularities. Or part same if we find function, if we find Taylor series expansion of that function, and in the principal part there are infinite number of terms, then we say that point function has an essential singularities. You see here, e raised to 1 upon z minus a, z minus a is a crucial point. If we apply limit z tends to a of e raised to 1 upon z minus a, it limit does not exist. So at the point z is equal to a, the function e raised to 1 upon z minus a has essential singularities. Okay, this is note is very important. There is a difference between limit being infinity and limit not existing. Okay, this is all about singularity of a function. In the next lecture, in the next part, we will see problem based on the singularity of a function. Okay, thank you.